Welcome once again, and I was discussing about regenerative braking. In fact, we have almost discussed it. I will just tell you the ideas here, no question of going. That okay, this was the motor. If somehow the speed become greater than ns, then generator mode it goes. Then it looks like this torque slip characteristics, whatever I am drawing, it will be like this from s equal to 0 to s equal to 2, between 1 and 2 it will be some braking mode it has gone, and if slip becomes, this is slip axis, if slip becomes negative, using that same formula, go on putting negative values and you will get a characteristics like this. Once again stable zone will be this, that. See, induction generator is not popular, it was not popular at one time. Nowadays once again interest is shown in induction generator because of solar conversion of power to AC system. Anyway, that is beyond the scope, but what I am telling, so far operation of this machine is concerned, it can operate as a motor between 0 to 1. Sometimes it may operate with slip 2 minus s when normal braking is executed, say plugging. Sometimes it may produce negative torque when it goes by regenerative braking. The term regenerative means this machine acts as now motor, it regenerates power and feeds it back to the supply bus, like that. But as I told you, with the advent of power electronic devices, the way you now execute braking, that may be also changed. I will give you simple idea. See, suppose you have got this supply, your 3-phase supply, rectifier and DC and 3-phase inverter. And I told you, you can both vary the magnitude of the RMS voltage and frequency, that is V and F can be varied depending upon requirements, you do it like that. And here is your motor and it is supplied. Induction motor. Now, suppose I say that machine is running and suppose the P is equal to 4, so that I can put some number F equal to 50 hertz. These are the nominal rated values, it is running. So, speed will be close to 1500 rpm, we know, no doubt, and it is running steadily. Now, suppose when it is running steadily like this, what I do, I decrease the frequency to 25 hertz. It was running, but here that frequency control, I reduce the frequency to 25 hertz. Should I decrease the frequency alone? No. Also supply voltage is to be reduced in the same proportion, so that flux remains same, that is one requirement. But in any case, frequency suppose I reduce to 25 hertz. Here the synchronous speed was 1500 rpm. Now, suddenly and machine was running at 1500 rpm, close to that, slightly below it. Now, suddenly you have made, suppose from 50 hertz, F you have made it 25 hertz. So, at what speed this synchronous speed, new synchronous speed will be now 750 rpm, is not? And rotor is running at 1500 rpm already, and stator field is 750 rpm. So, in which situation it has been put now? That rotor speed is much higher than the synchronous speed at which the field is moving when the supply is 25 hertz. Therefore, this zone, negative zone for this motor I must apply, and motor will give you negative torque. So, electrical braking once again can be implemented. I am not giving you, never think that this is the full scheme, but I am telling now with a very nice inverter supplying a induction motor, starting, speed control as well as braking can be done in much more elegant ways. Well, the methods we discussed, they are traditional, nice, it will give you better concepts, but also you keep now in mind that okay, I can do anything, voltage, frequency, everything I can change. As an example, it will immediately go to generator mode of operation. If you suddenly decrease the frequency to 25 hertz or anything, not 25 hertz, 50 hertz, 40 hertz like that, and it will develop different level of braking torque. And when you do that, you do not waste the kinetic energy of the rotor in some resistance or in friction. That energy will be pumped back to this system. Got the point? That is, it will feed back power to the inverter, whatever is supplying there. So, this, and then you read books and solve some problems, traditional problems, where we will be restricting ourselves. But so, 3-phase induction motor, remember there are 3 zones. This zone is then generating mode, and this is motoring 0 to 1, and then this is called braking in general, okay, in 3 zones in full scale, -2 to +2. S equal to -2 to +2. Anyway, you just have a idea of that. Now, after telling all these things, we will now go to another type of induction motor, that is called single phase induction motor, new topic. Single phase induction motor. Achha, just one comment about this generator operation, otherwise the discussion will remain slightly incomplete. For example, here I told this induction machine is connected to the bus and you can operate it as a motor. If there is no prime mover, NR will be always less than NS, it is operating as a motor. Now, remove the mechanical load, connect a prime mover, make its speed higher than NS, it will act as a generator. Is it possible to have to operate an induction machine as a 3-phase generator in isolation? What is a generator? I will have some field control, that is I will try to operate this machine, induction motor, this is the rotor, cage or whatever it is. I will drive it by a prime mover, can I expect some voltage to be generated? And here I will connect the load, 3-phase load. See, distinction must be made between these two cases. It is induction generator. After all, you know, diesel set, diesel generator often used. You run the prime mover, diesel okay, motor, IC engine, and you get supply and then load. No question of bus coming anywhere. So, can induction motor be operated in this fashion? The answer is yes, it can be operated, but as it is, if you connect like this, you do not expect any voltage to be developed. Remember that induction machine is a singly excited machine, is not? You give only supply to stator, no other supply is necessary. Therefore, to create the flux in the machine, that magnetizing current source must be provided. IM is necessary. In this machine, what happens? Will there be any voltage? Do you expect here? Yes, I may expect some voltage if you run the rotor, because of some residual field here. Some residual field was remaining on the stator iron, rotor iron, and you are running the rotor. A little voltage, maybe 5 volt, 6 volt will be generated. But story ends there, nothing more than that is going to happen. And if you don't have a residual field, nothing is going to happen. Why it will not going to happen? Who will create the flux? There must be some excitation provided to create the flux here. So, what can be done is that some capacitors are connected here, capacitor bank, appropriate value of capacitor bank is connected. I will draw it neatly. Suppose this is like this, you connect some capacitor bank in star, say, oh my God, capacitor. This is the rotor, and here is your generator output terminal. Understood? Across the stator terminals, you connect some capacitors of equal values in 3 phases. Then I am telling the observation, no explanation. Then you will say, you will see that for some values of capacitance, a reasonable voltage has appeared here. Okay? Because these capacitors will provide that initial excitation of the coil. But anyway, this generator is not very good. The moment you load it, voltage drastically falls. If time permits, I will discuss about that. But right now, what I am only telling is that an induction machine can be also operated as an induction generator, provided you make some arrangement so that the magnetizing current may be supplied to the machine. Okay? It is almost somewhat similar to that of a shunt generator, and it will be there. And when the machine operates in isolation, there is no question of calling it a synchronous speed. Bus frequency decides that. Those things are there, but just you remember only this much at least, that to create regenerative braking, machine must be connected to bus, and there is a definite synchronous speed. And if time permits, let us see induction generator, at least in open circuit, how you get the voltage. This can be also easily understood, but anyway, this is not very important. Now, the important topic is single phase induction motor. A single phase induction motor, constructionally, on the stator there is a single phase winding, and the rotor in general is a cage rotor. That is, it can be like this, a cage rotor, and a single phase winding, no R, Y, B, single winding. And in the way, if you see stator, suppose stator, there will be coils here, I am sorry, and let this coil be called M. We are calling ABC coil, let us call M. M will later we will say main winding. Suppose the name of the coil given to M, and on the rotor there is a cage rotor. That is the thing. So, a single phase winding motor will have at least one winding, call that to be winding M, and a rotor. Now, let me ask this question, that if this machine, if you connect a single phase source to this winding, what will be the consequence? Do you think motor will run? Do you think there will be rotor current? What is going to happen? See, the moment you have connected it to AC supply, this coil will carry current, sinusoidal current, and this current, it will create a field along this line. And this field, what kind of field will be created? We have seen standing pulsating wave. So, this flux will be this way, this way, this way, this way, amplitude is also changing like this. We will do that mathematics. In space, the field will be distributed in this fashion, is not pulsating standing. Will there be rotor current? Yes, because if you consider this turn through which there is a time varying flux, therefore, there will be induced voltage. Similarly, this coil conductor can be thought of another coil, all of them will carry current. It will just behave like a transformer whose secondary is short circuited. So, this will be there, and the rotor current then distribution, if at any time this flux is in this way, rotor currents will be cross, 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 other things will be dot, 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 dot. Following Lenge's law, it will try to oppose this, there will be also rotor field. But can these two fellows produce a torque? No, because the rotor field and stator field are acting along the same direction. Therefore, at least I can conclude this much, although the name single phase induction motor is there, I expect it will operate from a single phase source, and it is expected to have a single winding on the stator like this, and then I conclude, okay, if I supply this winding with a single phase voltage, no way, if the machine was stationary, initially machine was stopped, you have switched on the supply here, machine is not going to rotate. And this conclusion, therefore, people say that single phase induction motor, one big conclusion I am writing at the very beginning, induction, single phase induction motor having a single winding on the stator, single winding on the stator, has no starting torque, no starting torque, no way. So, it looks like the thing is nipped in the bud, what else. Now, the idea is that a single phase induction motor, I will show that although it has got no starting torque, somehow the experiment is, suppose by hand you make it run, okay, with some prime mover you give a start sufficient. By some external agency, if you start moving the rotor with this supply on, you will find to your surprise machine is picking up speed and will settle down to some final speed. In which direction it will rotate is decided by the fact in which direction you have given that spin initially by some external agency. If you give it a movement this way clockwise, you will find that rotor is now accelerating. Remove your hand and settling down to some speed. Similarly, if you have given a spin in the anticlockwise direction, you will find that rotor is accelerating once again and settle down to a final speed. So, very interesting that way, although the understanding is slightly difficult, is not. So, one thing is clear, a single phase induction motor has no starting torque. By observation, let us write like this, by observation, give, it will not, observation. However, it has got a running torque. That is the thing. Therefore, it looks like that a single phase induction motor, to make it work, it is no technical solution that you give a spin by hand or by some external agency. There is a motor, you switch on the supply, it must run. That is the whole idea. Therefore, you must do something with this motor, so that it is capable of producing the starting torque as well, by maybe bringing another extra coil on the stator. That is what precisely we are going to do. Therefore, to incorporate starting torque, I will bring another coil and show that it is a feasible scheme. And after machine has picked up speed, I know machine is capable of developing running torque, then I will disconnect that extra coil from the supply, and therefore, motor will finally run on a single winding, truly like a single phase induction motor, because we know single phase induction motor will have running torque. Okay? That is the idea. Achha. So, that way it can be done. So, before really going to the single phase induction motor, what I will first today tell you is that let us consider a two phase motor, two phase induction motor. It will pave the way to have a better understanding. Two phase induction motor, balanced, say balanced two phase induction motor. No problem. This is the rotor. Okay? And you have got two windings. Balanced two phase winding is what? Actual thing. This is suppose M coil, whose axis is like this, is not, and the other coil is here on the stator, whose axis will be like this, equal number of turns. So, this coil let me call M coil, and this coil let me call coil A, is not. And what I will do, it is a balanced two phase winding. So, stator has a balanced two phase winding, this, and arbitrarily I have called them coil M and coil A. Later we will call this as auxiliary coil. that is why A. Now, if these two coils are supplied with balanced two phase current, then it will produce a rotating magnetic field, is not. Therefore, this conductor coil and this current, that is I m and this is I a. Let I m is equal to cos omega t, and I am sorry, let I m is equal to I m max cos omega t, and I a is equal to I a max cos omega t plus 90 degree. We are telling 120 degree in case of balanced 3 phase. So, this is a balanced 2 phase current. Suppose I a max is equal to I m max. So, this m you remove, I max cos omega t, because these windings are balanced. So, balanced 2 phase supply you connect, these two coils will carry balanced 2 phase current. And then you can easily show, in fact, I told you to prove this, or earlier I have proved also, that a balanced 2 phase winding will also produce a rotating magnetic field of constant strength. Speed of that field is synchronous speed to f by p, supply frequency. Therefore, a rotating magnetic field will produced. In which direction it will move? From the leading to the lagging phase, all these things will remain, in this case in this direction, n s equal to 2 f by p. This is known to me. Therefore, once this field is produced, I am also telling several times, rotor is not at all aware of the fact that this rotating field has been produced by a 2 phase winding or a 3 phase winding. Therefore, the torque will be produced, I mean equivalent circuit can be drawn per phase in the same way as we have done in case of 3 phase induction motor, and motor will accelerate in this direction, and finally, it will settle down to a speed n r, and you can do per phase analysis. Okay? This current square R 2 dashed by S into 2 will give you the air gap power, that is 2 into I 2 dash squared means that reflected current squared into R 2 dashed by S will give you the torque produced in the machine, and so on. It will run as a balanced 2 phase induction motor. Balanced 2 phase induction motor are not popular, I mean 2 phase induction motor one can make it because supply is 3 phase. So, 3 phase induction motors are very popular. You can think of the fact that you have a 3 phase supply, and suppose fortunately or unfortunately you have a balanced 2 phase induction motor, you have to run it. What you will be doing? You require a balanced 2 phase supply. So, you must have read in your transformer connection, you invoke Scott connection, which will change that 3 phase supply to a balanced 2 phase supply, then connect this motor. So, in any case, that is another investment you have to do. Therefore, a balanced 2 phase induction motor is one which will work nicely. Its theories need not be separately told. So, per phase equivalent circuit you draw and you get away with it. In fact, those things have been done. Torque slip characteristics will be similar like this, S 0, S equal to 1, things like that. Is that clear? Therefore, this is the thing. But in a single phase induction motor, then how to analyze it? Another thing will be necessary to make a, I will tell you first the idea with which we will be doing. If suppose you have this knowledge will be necessary and I will apply that. Any unbalanced two phase current or voltage can be broken up, can be shown to be consisting of any unbalanced two phase current or voltage can be shown to be consisting of two balanced system, namely positive sequence and negative sequence voltage. Any unbalanced two phase quantity. It means that suppose there are two current, as you know, you must have applied, I am not sure, any three phase unbalanced current or voltage can be broken up into three balanced systems. One is a positive sequence, another is a negative sequence of balance, another is a zero sequence. So, if a circuit suppose is energized from a unbalanced three phase voltage, how to find out the currents in the circuit? What I will do? I will break it up into a balanced three phase positive sequence system, find out the currents for that, which is easy to find out. I will apply the balanced negative sequence. Negative sequence means if it is ABC sequence, that will be ACB sequence. I will find out the current for that, and there will be zero sequence where they will be all co-phasal, and for that also I will try to find out the currents in the impedances and add them up to tell you what will be the resultant current. In case of an unbalanced two phase system current voltage, there is no zero sequence. So, suppose what I am telling is that consider this motor only, which has got two windings, and I suppose I sometimes drawing it here. So, let me draw it here. This is the main, this is the A winding. Suppose this current is IM, okay, this current is IM and this current is IA, and this current need not be balanced two phase current. Then what I am telling, this currents IM, suppose these two coils are excited by currents which is unbalanced. Suppose IM and IA are unbalanced, means what? Their magnitudes may not be same, the angle between them is not 90 degree, then only it is unbalanced. Then IM can be written as IM1 plus IM2. This is the positive sequence of IM1, this one negative sequence, and auxiliary winding current, that is this current, is IA1 plus IA2. Therefore, the whole idea is, because single phase winding machine, let us assume even if the auxiliary winding is not there, let us presume there is another coil here. To analyze this situation, only main winding present, I will excite this, and I will pretend there is an auxiliary winding, but it is not excited. So, this and this are same, na? IM is there, auxiliary winding, IA is 0. what is the point of its being there or not. Okay. Anyway, we will discuss it in greater detail in the next class. This is very interesting topic. Thank you.